Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to wrap up our discussion of the derivative section of calculus with the antiderivative. So the entire idea of the antiderivative really comes from the thought of, if we have the derivative operator, d over dx, can we have an inverse operator? Or can we undo that process? I mean, we have multiplication, we undo it with division. We have exponents, we undo that with roots. We even have exponentiation, and we undo that with a logarithm. So it makes sense to think through it, and sure enough, the idea actually does have a lot of merit, and it does work, because when we look at the graph of a derivative, because we know how the derivative comes about from the original function, we can recreate that original function's behavior based on what their derivative does. And just like we can take a derivative multiple times to get a second derivative and a third derivative, we can take an antiderivative. One of the classic examples of this is, again, we're talking about position, velocity, and acceleration. If we know the acceleration of an object and we know something about its position in time at any point, we can actually work our way backward and create a formula to describe its velocity over time and its position over time, all from that little bit of information by using the antiderivative. So real quick, the particulars here are that f is the antiderivative of lowercase f on the interval I if the derivative of capital F is equal to lowercase f. This is no different than saying that 6 divided by 3 is equal to 2 because 2 times 3 equals 6. Now, a couple of things you need to be aware of, though, is that, remember, we had the situation where if we shift a function vertically, we do a vertical transition, the derivative isn't going to change because the derivative is the slope, and that derivative will be parallel whether we move that function up or down. Changes nothing about the situation. So we have to account for that when we take our antiderivative if we're looking for specific functions or specific values and not simply an antiderivative of a specific term within our function, okay? And to do that, we simply introduce that there may or may not be some constant. And this is why I mentioned that we need to know some information about the thing we're looking at, the system we're looking at, in terms of what it would deal with for the antiderivatives. We'll look at an example, and that'll make a lot of sense, okay? Now, one of the things to be aware of here is that when we say f of x plus c, this could be any c that is an arbitrary constant that works for our system. Typically, these are going to be real values, but there are situations where these could be complex values. And this does not have to be positive. It could very well be negative. Additionally, when we say generically c, we could have a situation where this could be multiple different values depending on the situation. So you'll notice the note I have down here talks about sometimes when we take an antiderivative, we end up with a situation where we can have a piecewise function. A great example of this is if we're talking about f of x being 1 over x. The antiderivative to this is not actually the ln of x, it's the ln of the absolute value of x, because you can have the natural log of x pointing to the right, you can have the natural log of x pointing to the left, and the derivative of that will simply be 1 over x. Becomes a pretty big deal here, right? So when we're looking at this and we're trying to work our way back up from here, because this exists on both sides of 0, we have to construct the piecewise function. Now, typically, we'll simply write the ln of the absolute value of x. We don't have to write this because remember that the absolute value is also a piecewise function. But this is just an example of how this actually would be. And there are other situations where this comes up, typically with rational functions. But anything where you're going from like an odd degree to an even degree, or any situation in which your derivative exists in a section where the antiderivative does not exist on that domain as just the function, is where you're going to have to use a piecewise function instead. So the thing I say here is always check the graph of your f of x when you're doing your antiderivative, just to make sure that you don't have a situation where you may have to shift things in order to account for that negative that wouldn't be there normally. You can think of this like how whenever we take the square root of x, we have to write plus minus in order to deal with the fact that we might be dealing with the upper curve or the lower curve. Similar here. We do this even though typically we only deal with the positive. We do have to account for the fact the negative could be there. Now, let's go ahead and look at just like some examples of what these look like. But honestly, the entire idea is just think your way backward. Just do it in reverse. So here is a small chart of examples. Now, there are bigger charts and there are other places where you can memorize a function and its antiderivative. I do not find that to be very useful for anything beyond the complicated trig functions. So those trig functions where I don't even necessarily remember what the derivative of the trig function is, like hyperbolic functions and so on and so forth. For most of these, if you know what the derivative of a function is, then I find you are far better to be able to work backward to construct the antiderivative. For example, when I do 4x squared, if I want to take the antiderivative, I don't go up and do it in this manner, although it is similar to this. I think, what would I have to take the derivative of here? Well, because this is a power, this got reduced by 1, and then I brought the 3 down here. So that means I need the opposite. I need a 1/3 to take care of that 3, and then this would increment up, which is what this is showing you. But for me, the difference is memorizing a formula versus working through a procedure that you are going to be able to recreate for even more complicated situations where you may need to alter things or change things based on what's going on. Okay, and then I put the sign up here, sine and cosine, but you'll notice down here we talked about secant squared, and that's because we know that the derivative of tangent is secant squared, so the antiderivative of secant squared would be tangent, and I just left off the plus c here because we were talking about these particular ones. I put the c here to highlight one important point. When I take the antiderivative of f of x, I'm going to get f of x plus c. And when I take the antiderivative of g of x, I'm going to get g of x plus c. So generically, I can combine those c's into a single c in order to not have to worry about it. Now, sometimes you might want to keep them separate when that's useful, but those will be specific cases. And these are all easy, generic derivative rules, and then the antiderivative version. You can do this same thing with all of the other rules, like the power rule, the quotient rule, and the chain rule, but it gets a little bit more complicated, and we look at that in the next section when we talk about integral calculus. So let's just look at an applied example, and then you'll get a couple of examples to work on. So as kind of a callback to one of our first videos, here's a physics problem. Now, we're going to go ahead and assume that the acceleration due to gravity is 9.8 meters per second squared, or 32 feet per second squared. That's pretty standard for these introductory style calculus problems. In this situation, a ball is thrown upward with an initial speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Find the maximum height of the ball and how long it takes to reach that height. Also, when does the ball hit the ground? You can do this with algebraic equations if you know all of your kinematic equations. However, simply knowing those pieces of information and that, you can derive all of the information you need to solve this problem using calculus and the antiderivative. Go ahead and see if you can do that now, and I'll show you how it's done in 3, 2, 1. So for this, we knew that our acceleration was a simple constant, 32 feet per second squared. Now, I went ahead and said that because it's falling, that's going to be down. Oftentimes, for sake of ease in physics, they'll call that positive. It really doesn't matter because in the end, your numbers should work out for situations like this. There are specific times where you'll want to be careful with that. So we know that the velocity is the antiderivative of the acceleration. So when we take that antiderivative, we get negative 32t plus c, and this is where we need that initial information. And it doesn't have to be at time 0. We could have had any time here, as long as we had some piece of observed information, a time and a velocity. So from that, we got that c was 48, and that allowed us to then go ahead and solve for the maximum, because remember, that's where my derivative is 0 for my position function. So my maximum position was when my velocity was 0, which happens 1.5 seconds after we throw the ball. Throw the ball up, 1.5 seconds, it peaks, and then it falls all the way to the ground past the cliff, right? So we then take that function here, and we take its antiderivative, and we get negative 32 over 2t squared plus 48t plus c, which simplifies itself to be the negative 16t squared plus 48t plus c. Plugging in our initial value for the height, which is 432 feet, where we released the ball at time 0, got us. Now, when you solve through here, you'll actually get the plus minus situation. But again, remember, when we're talking about time 0 is when we started observing. So negative time would be time before we started observing. And for some situations, that makes sense as long as we know that whatever the process is that's going on is continuing. So if we know that we have a repetitive continual process and we're observing at some point in there, negative time possibly makes sense. But in this situation, since the ball was thrown at time 0, we can throw away the negative answer and simply keep 6.9 seconds, meaning the ball hits the ground 6.9 seconds after it was thrown up in the air. And then to solve for what the maximum height is, we simply take that time that we found, plug it into our position function, and we get that s of 1.5, so the position of the ball at 1.5 seconds, was 36 feet positive, so 36 feet up in the air from where we threw it. Now, you could add that to the height of your cliff as well. It's perfectly fine. So depending on how you wanted to do it, you could have, instead of getting the answer of 36 feet, you easily could have had the answer of 468 feet if you're measuring from the ground, which I believe this function would give you that position from the ground. I gave the height from the throw. And again, that would really depend on what the question is asking. It would probably be, I would hope, a little more clear on a test about when it says the maximum height of the ball. Probably would say from the ground. So I'm going to give you a couple of problems that you can practice just simple antiderivatives, both from going second degree and first degree. And that'll be it for this section. So I hope this overview of the antiderivative helped. And as I said, in the next video, we're going to start looking at integral calculus, which is where we're going to be using these antiderivatives a little bit more. If you have any questions, feel free to drop into the comments or join us on Discord. And as usual, the answer to the exercises will be after the outro.